So FEA has a very rich mathematical, basis. So let's look at like a very simple, physical phenomenon that can be modeled using a simple equation. Spring mass, right? A mass is attached using a spring to a fixed base. Now I move the mass, and what is the deflection in the spring? That is the question. So there are three things here. Like, what is the deflection X? What is the mass? What is the stiffness in the spring? Okay, and what is the force? The force here will actually be the mass, but you can apply additional force using like by pulling them. But the basic things are, what is the force? What is the stiffness of the spring? And what is the extension? And the equation for this is F equals Kx. Force is stiffness times the deflection. So the stiffness is characteristic of the spring that we have here, and it does not change. And the extension in the spring is directly proportional to the force we apply. So if you apply 2F force, it will be 2F, 2X, 3F, 3X, 4F, 4X, and so on. So let's say that you know the force that is applied or the mass that is attached to the spring, and you know the stiffness of the spring. How do you calculate the displacement? It's simple. You just invert the k, and then it's x equals f by k, or k inverse into x. So this is the most simple equation that we have to derive or extract displacement from the physical event. Now let's look at a more complex discrete system of springs. Now we have two springs instead of one, and we have 1, 2, 3 forces and 1, 2, 3 displacements, and we have 2 spring coefficients of stiffness. In a scenario like this, we actually use the conservation of energy, or we just look at the force balance. All the forces cancel. The sigma fx will be equal to 0. That's what we look at. So if you look here, the force F1 will be a combination of K1U and minus K1U2. We do the minus here because we are actually removing this effect on this spring. And we write equations like this for each one of these forces. And if you look at these 3 equations, they can be easily separated and written in matrix format like this. And once we have this matrix format, if you look at it, it's it can be simply written as F equals K into X. And if you want X, then you just invert the K. Now this is a discrete system of springs, and you have to remember this, because whenever we have like even a complex setup like this, where we have multiple spring stiffnesses, multiple forces and displacements, if you can arrive at this particular form, then it will be very easy for us to determine what the displacement is going to be, because we can just invert the K. And the point I'm trying to drive at is because even computers will find mathematical operations like this to very easy to perform. And this is important because if you look at something like this cantilever bar and with an axial load, the bar is attached at one end, it has length L, and we are applying a force P axially, so that it deforms in one direction only. Now, how do you extract or find out or determine the extension in the bar in a continuous system like this? If you see here, this is a discrete system. So all the forces, the displacements are being applied at like points 1, 2, and 3. But here, you can't say really that the force P is being applied at just this point. No, this is a continuous system. The whole bar will be under that load. So how do you model the displacement here? What is the equation that we use? And how can we solve it, or how can we bring that to F equals Kx? So for that, we actually look at something called a minimum potential energy, a different form of a conservation of energy. So basically, what is equilibrium, right? We have 3 load cases here, 3 cases here. We have a ball. Let's say it's a small ping pong ball that you drop in a bowl. When it's at like the top here, it's not stable. It's going to roll off to the center of the bowl. So if you put it here, it will be called an unstable equilibrium. So, but if you just drop the ball in the bowl and let it, roll around for a while, it will finally settle here at this point. And this point we will say that the ball is at a stable equilibrium. Now, let's say the ball is just sitting on a table that is very flat. So it doesn't matter where the ball is, right? You can push it around, but all the points will be considered a neutral equilibrium. Now, we are mostly concerned with the case A here, the stable equilibrium, because in a conservative system, the total potential energy of the system is equal to work done by all the forces. It's work done by internal force, it's work done by external force. But whatever forces you apply, it will be conserved. And in a stable system like this, the change in the total energy will be zero. So there is no, at this point, there is, if you put a force, like you apply a force on it, it has to be absorbed by the body. But you won't be seeing any change in the total potential. And that's what we are looking at here. And we are solving for change in the potential energy equals zero. And if you look at the change here, wherever the potential energy is hitting like either a maximum or a minimum or like an inflection point, like a change from, that will be where your equilibrium change in potential energy is zero, and that is where you have your stable equilibrium. And this is actually used for solving scenario like this. So if you look at it here, we look at the force applied on the body. You're actually pulling the rod in one direction. So that will be force that is applied on the body. Now, in a stable equilibrium, like the work done by external forces and the work done by internal forces equate total potential energy. And in a stable equilibrium, the change in the total potential energy will be zero. Now, the work done by external forces can be modeled using the integral of the force into the displacement. And the work done by internal forces can actually be calculated using the strain energy of the system. The strain energy can be calculated as an integral of the stress in the displacement. And when you apply the the delta PE equals zero, we actually arrive at this. And this is, if you look at it, it's an integral, and you have a differential here and a double differential here. This will be very complex for for us and for the computers to solve. And again, we are trying to go back to a simpler world here, where we can just treat it as a discrete system of springs, and we can arrive. How do we go from a complex equation like this to a simple equation like this? And we get help from Rayleigh, the Rayleigh Ritz method, where he says that if you have like a function like this, like u, what you can do is you can just approximate that. Instead of integrating it, you can use a function that minimizes. And that function, you can select any function that solves the boundary conditions of that system, and and it has to have adjustable constants. And once you have such a function like this, you can just do like apply the stable equilibrium condition. The change in the potential energy equals zero, but we are just integrating it using the adjustable constants. And that will help us to find the displacement in the body. If you look at the function here, we are just using this function to approximate this displacement in the bar. And the more terms we have in this function, the better the solution of the. We use this Rayleigh Ritz method, and we derive the finite element form of the Rayleigh Ritz method. And we again use the function here, but instead of using just one element, we actually use three elements. So we just divide the bar into three elements, and for each bar, we actually did come up with a function. And from that, we can actually derive like a function for the displacement. And once we have the function, then we go back again to apply the change in potential energy equals zero, and then we can derive the form that we are looking for, k into d or x equals x. Once we reach this form, we can just simply invert the k, and we can find the displacements. And the displacements will further help us, find the strain and the stresses. So the beauty of this finite element form is that no matter how many displacements you have, how many complex elements you have, right? We still come back to this same formulation. We just apply it for each displacement and each force. So there are different element types that we actually use in finite element method. There are one-dimensional, two-dimensional, three-dimensional. In three-dimensional, two-dimensional, we have triangular elements or tetra elements or quadrilateral elements. In three-dimensional, we have these tetrahedral elements, and we have these quadrilateral elements. So no matter what the element type is, we still come back to this same form, right? F equals K, and we find that out for one element. And then if we have a bunch of elements, what we do is something called a stiffness matrix assembly that goes like this. We know the positions of the displacements at each common point, and we actually add up the K1, K11, K12 constants here to derive the final displacement, stiffness matrix assembly. And once we have the global stiffness matrix, we again come back to the same Kx equals F equation. We invert the K to find the displacements and subsequently the strains and the stresses. So it's basically like saying this, right? We master all these finite element method, and we understand this concept, and we formulate these elements. These elements can be anything, like they can be 1D or 2D or 3D. But basically, you're saying, I'm trying to formulate these elements. I'm building something I know. I'm taking something I know to build a model that behaves like a real thing. So this is a car, but it's not actually a car. Made up of like all these Lego pieces. But each individual Lego pieces, we know exactly how to formulate that and how to get the displacement and forces from them. So we are taking those small components, build this model, and then we use that model to actually do the crash analysis. So we swap out the Lego bits for finite element elements, right? So we formulate finite element, different 1D and 2D finite elements, to create a finite element model, and then use that model to create the crash analysis. From an industry perspective, on a daily basis, what a user does, a CA engineer does, is build the solver model on his workstation using, like a pre-processing software like HyperMesh or ANSA. They build the mesh, they build the finite element model, and then they run it not on their workstation, but on high-performance compute cluster, because some of these models will take days and months to run if they run it on their workstations. So they run it on high-performance computing clusters, which take each job can take anywhere between 48 to 224 to 448 CPUs to run in like 24 hours. And then once the results are complete, they again post-process these results on their workstation. So we'll briefly look at what Abaqus FEA software is and what its capabilities are. And we are borrowing examples from earlier. So the main type of analysis that Abaqus is capable of is implicit, explicit, multi-physics, and model analysis. Again, implicit means physical events that can be modeled over like an extended period of time. Or in other words, we are saying that time does not really have an effect on it. So let's say you are taking an example like this, right? And you are just looking at the deflection here. We are just putting a load on this, and it doesn't matter. You can do it over like 1 second, or you can do it over 10 seconds. The deflection is going to be more or less the same. Whereas in explicit, you are looking at very high speed, high deformation events, like blast scenario, like a simple small detonation can take place in milliseconds, and in such cases there will be a lot of deformation that is involved, and to capture that we need to take into account the inertia effects of it. So it's really time dependent, and they can be modeled using the. And when it comes to multi-physics, we are basically coupling the structures part of simulation to maybe some fluid interaction, or we are looking at like a thermal expansion, and then we are looking at how the structure is deforming under such interaction. So if you look at this particular example here, so we are looking at how the fluid is responding to like a small pellet that is going through the tank. And then we are also looking at how the base of the tank is undergoing stresses due to the movement and the interactions above. And coming to modal, in modal analysis, we do sort of a frequency extraction. So again, every body has, its own natural, and every force or every load that you apply on a body will invoke its own vibration. When the natural frequency is matched with this, the vibrations coming from the force, it can, result in resonance, where the body will vibrate, at an amplified manner. And such amplified vibrations can cause failure in the body. So basically, in modal analysis, we are trying to look at the natural frequencies of the body. We extract the natural frequencies, and we make sure that those natural frequencies are not, low like 15 hertz or 20 hertz, and that they are high like 200 or 500 or 1000 hertz, depending on the application, so that it does not cause premature failure in that body. So no matter what the type of analysis is, the components of an Abaqus model are, again, the geometry of the model, how thick the body is, how many elements will we have in this bar, and so on. The material definitions: what is the material of bar? Is it steel or is it aluminum? And boundary conditions: where is the bar attached? Can it move in X? Can it move in Y? Is it fixed? Etc. What are the loads on the body? Here we just have one axial load, and that will be contact definitions. This is a fairly simple model, but so let's look at this. Here in the contact analysis, we actually have this ratchet that's moving, and we look at the contact here. So in cases like this, we also have to model the contact in the Abaqus model. So that will be another component of your Abaqus model. And finally, like output request. Like once you apply all these components and you run the simulation, like what are the output that we are looking at? Like in a simple model like this, we are just looking at the displacement. But let's say in a crash analysis, we are looking at the deformation. Or in an analysis like this, we are looking at the contact stresses here. Like when this piece comes into contact with this piece, what is the contact stress, and can that contact stress actually cause failure in that body? So depending on the type of simulation, we actually modify the output that we are looking at. So this is a look at the Abaqus GUI, the graphic user interface. And you have a very compartmentalized approach to the interface. So like we look at the various components of the Abaqus model earlier, and so we have this drop-down model, so where we can switch from one module to another. So basically, if you are doing the geometry definition, you go to part, and you'll have a context menu like this to create the part, and then next, the properties, when you want to define the material of the body, you will go to the properties module, and so on. So you have a very compartmentalized and very intuitive interface to build your Abaqus model. Let's look at the scope of the course for finite element analysis using Abaqus. So in this course, basically, we will be looking at the basics of finite element method. Like I said, it has a very rich mathematical basis, and we'll start with the Rayleigh Ritz. We'll solve problems using Rayleigh Ritz, and we will derive the finite element model from the Rayleigh Ritz method. We will look at the stiffness matrix assembly. We will look at, we will derive the stiffness matrices for 1D elements, 2D elements, and 3D elements, stiffness matrix, and finite element method for beams, and then we will take a look at the isoparametric elements and Gaussian quadrature. That will be like the math portion of the course, and coming to an application part of it, we will use Abaqus finite element code to build FE models, like implicit models or explicit models, and model analysis models. You will be able to, at the end of the course, you will actually be able to like build models. Take an example, take a research paper or a test scenario, and actually model that test scenario using the different analysis procedures mentioned here. And the final project for this course will be to The user will be able to select a load case of their choice and actually build a correlation model using Abaqus. Thank you.